Good evening. As you may know, Brian Jones and myself have been working hard to save the Yearbook of Astronomy. Our first edition was published in April 2017. This book is a limited edition, 800 copies, and I'm sure that it will be worth a good sum of money in the future. The yearbook has been selling well, and we have just a few copies left. If you would like to buy one and help save Patrick Moore's Yearbook of Astronomy, please follow the link below this video program. Also, we have finished work on the 2018 Yearbook of Astronomy, which is now with the publisher and will be published this November. If you would like to pre-order the yearbook, please visit the Amazon website. I should add that the yearbook is also being published as an ebook for worldwide distribution. Now, to celebrate the first anniversary of NASA's Juno spacecraft's arrival at Jupiter, which was on the 5th of July 2016, we take a look at the latest images and science results. With a diameter of 143,000 kilometers, the planet Jupiter is the biggest planet in the Sun's family, and is the fifth planet in order of distance from the Sun. Jupiter is flattened at the poles due to its rapid rotation. The planet takes just 9 hours, 55 minutes to revolve on its axis, and Jupiter takes about 12 years to orbit around the Sun. The planet has been visited by a number of spacecraft since 1973, starting with the Pioneers 10 and 11 in 1973 and 1974. Then Voyagers 1 and 2 in 1979, followed by NASA's Cassini and New Horizons spacecraft as they journeyed out to Saturn and Pluto. We take up Juno's story at Cape Canaveral on the 5th of August 2011. The spacecraft is in its deployment pod on the top of an Atlas V rocket, one of the most powerful rockets in NASA's fleet. It is 4:25 p.m. and Juno is about to launch on its 5-year journey to Jupiter. Jupiter has huge powerful radiation zones around the planet, which could damage the sensitive science instruments carried by Juno. So we all held our breath in the final minutes leading up to JOI, Juno Orbit Insertion.
Systems, this is Nav.
Go ahead, Nav.
Yeah, we see the expected sharp shift upward and the Doppler residuals indicating the main engine has started.
Copy that. That's good news. We're still awaiting confirmation of that in the tone. All stations on Juno Core. This time we see the tone for minimum burn timer. Almost there. All stations on Juno Core. We have the tone for burn cutoff on Delta B. Gratuito mum Juno. Welcome to Jupiter.
Burn time was 21:02 seconds, only differing 1 second off of the pre-burn predictions.
What a feeling. A mission of this complexity to accomplish tonight is just truly amazing. And it really highlights the partnership and the teamwork between NASA and our contractors and our partners to be able to achieve this amazing, amazing mission.
So tonight, through tones, Juno sang to us, and it was a song of perfection.
The team, the amount of time and effort everyone put into this, and the risks that were overcome, it's amazing. I mean, the more you know about the mission, you know just how tricky this was, and to have it be flawless, I mean, I really can't put it into words.
You see a handful of people up here, but what we represent is a team of almost 900 people that built and launched Juno, and roughly 300 people that operated it and got us all the way through into Jupiter orbit tonight.
Putting an orbiter around Jupiter is, that's the reason we all go into this profession. It's science fiction, and yet it's fact.
You get a really great, dedicated team of a lot of people working really hard for a really long time. You can do some amazing things.
NASA did it again. We're in orbit. We conquered Jupiter.
The science experiments can now begin to survey the planet's powerful magnetosphere, the chemical elements in Jupiter's huge atmosphere, and of course JunoCam, which will send back wonderful images of Jupiter's cloud tops and, in the last few days, Jupiter's famous Great Red Spot.
Okay, thanks, Diane. It's great to be here. It's exciting to be able to share what we've learned from some of these first passes by Jupiter. And I'm really excited to tell you all the news that we've got. So I'd like to talk first to the first image, Scott Bolton 1. And so here I'm going to illustrate really how Juno works. So Juno flies over the poles of Jupiter, and it goes very, very close to Jupiter, just within a few thousand miles of the cloud tops. It's traveling very, very fast. It takes only about 2 hours to screen past Jupiter. So the way it really works is every 53 days we screen by Jupiter, dropping down from the North Pole and going out of the south. And we're going so fast that that whole pass from North Pole to South Pole is about 2 hours long. And most of our science is collected during these very close passes. And that's really what's unique about Juno, is because we get so close to Jupiter and we cross over both poles that allows us to see very new things and unique things about the interior and how the magnetosphere works. And so today, what you'll hear is what we've really learned from our first 2 close passes by Jupiter. We'll also share some more recent data, including our latest images that came down last week, some observations of interplanetary dust and Jupiter's rings, and you'll hear some recent sounds from Jupiter that are actually quite unique. So as I go through this, the general theme of our discoveries is really how different Jupiter looks from what we expected. So Juno, in many ways, is looking inside of Jupiter for the first time and close up and personal. And what scientists expected was that Jupiter was relatively boring. It's uniform inside. And for decades, scientists have assumed this, that if we drop below the cloud tops, below where the sunlight reaches, that pretty much Jupiter was all uniform inside, and it really didn't matter where you looked, it would all look the same. And what we're finding is anything but that is the truth. It's very different, very complex, and we're going to share those with you today. So I'd like to go over to slide 2, Scott Bolton 2, and here you see an incredibly beautiful picture of the North Pole of Jupiter. This is created by amateurs that sign on to the Juno website and make our images for us. This one's unique in the sense that each time we pass over Jupiter, because we're going over the poles, it's half sunlit, half dark, half night side. And what somebody has done here is they've actually stitched together pictures from different close passes of Jupiter so that you could see the whole thing sunlit. And what you see is incredibly, just complex features, these cyclones and anticyclones all over the poles. That wasn't really expected. The bluish hue is probably real. And the biggest feature is that Jupiter from the poles doesn't look anything like it does from the equator, or from what our usual picture of Jupiter has zones and belts, the great red spot, and we see these stripes, and that's the Jupiter we've all known and grown to love. And when you look from the pole, it looks totally different. In fact, if you look at this picture and somebody had shown it to you a few years ago, I don't think anybody would have guessed this is Jupiter. So the fact that there are the number of cyclones that you see at the poles is really something new that we didn't expect, and the fact that the North and South Pole don't really look like each other is also a puzzle to us. And so scientists are working to try to understand how these dynamics work and why Jupiter looks the way it is. And of course, we're also wondering whether this is a stable configuration. We've only gone over a couple times, and the question is do these storms or cyclones that we see here, are they stable? Are they going to stay the same way for years and years, like the Great Red Spot, which lasted 300 years at least? Or is this something that's dynamic? And of course, only time will tell us which one is true. Okay, so the next slide, slide 3, Scott Bolton 3, shows you a scientific and artistic expression of what the inside of Jupiter might look like. And so these are cutouts of Jupiter from the top all the way down to the middle of the core. And this represents what a lot of scientists believe Jupiter looked like even before Juno got there. In fact, a lot of our mission was based on some of these kinds of figures. And what Juno is about is looking inside of Jupiter pretty much every way we know how. So we have 3 different techniques to look into Jupiter. One is the gravity field, which sees all the way down to the bottom where you see ice rock core. And you're looking at like 40 megabars, 40 million bars of pressure. And 1 bar of pressure is what we feel at Earth at sea level. So that's the atmosphere of the Earth at sea level pushing down on you. So in the middle of Jupiter is a much, much higher pressure. So if there is an ice rock core, the rocks at the middle of Jupiter don't look like the rocks in your backyard. We have a magnetic field experiment that looks into that bluish region that's called metallic hydrogen, and that's where the hydrogen is squeezed so deep, so much, and the temperature is such that it actually behaves more like a metal, and it's like a liquid metallic hydrogen, and we believe somewhere in there maybe the magnetic field gets created, or maybe above that where there's enough charged particles. But the magnetic field kind of penetrates into that. So, and then at the top part of the atmosphere, just on the right, you see a cutout called meteorological layer. That's sort of the upper atmosphere where the clouds and the upper atmosphere is dynamics. It's actually quite deep. It goes down hundreds or even 1,000 kilometers deep. And we've never seen that. And we have a new instrument that was pretty much invented for Juno called the microwave radiometer, or MWR, and it looks into that region. So we have these 3 ways to look into Jupiter. The top part is done with the microwaves, the middle part is done with the magnetic field, and then the gravity looks all the way down to the center. And so now what I'd like to do is show you a little bit of the new data and what we've learned from this MWR the first time we passed through. So go to Scott Bolton, slide 4. And so here you see on the left-hand side an image of Jupiter from Cassini, I think it is, and it shows you the Jupiter that we all are used to, the zones and belts, the stripes, and then you see the great red spot. And on the right-hand side, you see some of the new microwave data. And what you're looking at here is that at the far right side of that, the top of it, is sort of the cloud tops, and then the part that turns orange at the bottom of it is looking deep about 350 kilometers down. Now, in between that, what you see in the red, the white, and a little bit of bluish hue, those are indications of how much ammonia is present, or the abundance of ammonia. So orange means it's very abundant, yellow means a little bit less, white is even less than that, and blue is the least amount of the ammonia. And so at the top, there's very little ammonia, and the ammonia starts in. But the most startling feature of this that was brand new and unexpected was this sort of column that you see of orange, where you have a band of ammonia around the equator of Jupiter. It's in the zone, it's very deep, and in fact, this was completely unexpected. You have a deep band of ammonia that goes from the top of Jupiter as deep as we can see. I mean, it goes down to 350 kilometers here because that's the limit of where we're looking. It may penetrate even deeper than that. And so that was a new thing that we learned just when we first looked at this data and saw it for the first time with MWR. The other thing that's new about this is that in general, you see that the ammonia peaks across all latitudes pretty deep, all the way at the bottom. And what scientists had expected was that that would peak and be uniform much further up, near where we thought the ammonia clouds were going to be forming. And then finally, you see that there's a lot of variation with the ammonia in latitude. There's some bluish parts in the mid-northern latitudes. There's different yellows and oranges that are showing up even at the high latitudes. And what this is telling us is that Jupiter's not very well mixed. It's not all uniform inside. The idea of once you drop below the sunlight that everything would all be uniform and boring and mixed up was completely wrong. It's actually very different depending on where you look at. And this is a brand new result. And this, in fact, addresses some questions that we've had for decades. About 20 years ago, we sent in the Galileo probe into Jupiter to measure its composition and to learn about its atmosphere. At that time, scientists thought that once you went through the cloud tops, you would basically see the same thing, and no matter where you looked, it would look the same. But in fact, it came back with surprising results that people didn't completely understand, and one of the assumptions was that the Galileo probe just happened to go into a warm spot, and in fact it did look warm where it went in, and maybe that was unique. And what we're finding is that many parts of Jupiter are unique, and if you had stuck in 3 or 4 probes into Jupiter in different places, you very likely would have gotten 3 or 4 different results, and you wouldn't have necessarily known what to make of it. And so only through this new look that we see with MWR do we realize how variable this giant planet really is beneath its top layer of clouds. And that's really going to force us to rethink not only how Jupiter works, but how do we explore Saturn, Uranus, and Neptune if they're highly variable like this. We may need some kind of technique like Juno, or maybe the next generation of these kinds of things, where we can look beneath the clouds globally to understand how things are varying. You'll also note that the whole signature of the zones and belts doesn't seem that apparent in our data, and that puzzled us and surprised us. So the zone and belt structure either doesn't penetrate all the way down, but you can see there is some structure, it just doesn't correlate to the zones and belts, and so it evolves to something new inside of the planet, other than maybe right near the equator where that ammonia band is. And so that was a surprise to us, and we've learned that these zones and belts, either don't exist or this instrument isn't sensitive to it for some reason, but we don't understand why it wouldn't be. And so you really see this new picture of Jupiter in this data, that it's very dynamic underneath the surface of the clouds as you penetrate down, and there's this strange band at the equator. Now, we have it almost looks a little reminiscent to the Earth. The Earth has something called a Hadley cell, where we have a tropical band around the equator, and then we have the subtropics just above that. Those are dry, the tropical band is moist. Jupiter looks a little bit like that in this ammonia, but it couldn't, is unlikely for that to have worked the same way the Earth does. The reason the Earth has a tropical band is there's a surface underneath the atmosphere that allows for a return flow. And so that, you either have an ocean or land underneath, and that allows for us to create these cycles and circulation cycles and create these dynamics at the Earth. Jupiter's gas all the way down. So while it might look a little bit like the Earth, it can't be working the same way. And so that was a big surprise to us. It is possible that this band penetrates all the way down into the middle of Jupiter. I mean, we don't know. And eventually, when we combine all of our magnetic field and gravity field science and get more microwave science, we may be able to tell something about how this band is working and how it's being formed. Okay, so I don't have another figure for this, but I wanted to touch on the gravity field, which I think there's sort of a general theme that we're seeing, that the inside of Jupiter works very differently than people had assumed. It's much more complex, and there are motions deep inside that people hadn't anticipated. And the gravity field is consistent with that. When we went to go measure the gravity field, what we were really looking for was the core, whether there was a compact core or no core. And instead what we found was that it really looks fuzzy. There may be a core there, but it's very big, and it may be partially dissolved, and we're studying that, but that came as a big surprise to us, that there was no core. Now, these mysteries that have to do with the interior extend into our magnetic field experiment, and I want to turn it over to Jack Canerney, my colleague, who is the lead for the magnetometer experiment, as well as the deputy PI, to explain the magnetic field discoveries.
Thank you, Scott. I'd like to start off with the magnetic field observations. First off, the magnetometer is it's like a fancy compass, an electronic compass. It measures both the direction of the magnetic field, like a compass does, and it also measures the amplitude or the magnitude of the field. Now, the Earth's magnetic field, we have a pole in the north and a pole in the south, and in between it varies little. Wherever you go on Earth, the compass needle does not deviate very much from north or south. And that was kind of our expectation for Jupiter before Juno's observations, based on our knowledge from spacecraft that passed not so close to Jupiter. And Juno really is the first time we got in close, very close to the surface of Jupiter. And what we found in our first few passes is that the magnetic field was both stronger than we expected, where we expected it to be strong, and it was weaker than we expected when we expected it to be weak. In other words, it evidenced a dramatic spatial variation that we were not quite aware of previously. To illustrate that, I'd like to turn to Jack 1, which is a figure drawn up by our grad student up at Harvard, Kimmy Moore, and she's represented on this sphere the magnetic field that we expected at Jupiter, and those are the contours that extend from left to right, the red positive contours up north and the blue negative contours down south. On top of that globe, there's a trajectory, the subsurface latitude and longitude of the spacecraft during PJ1, and those 5 groups of different colors represent the kind of addition to the magnetic field that you would have to make to follow the field along the trajectory. So it just illustrates the spatial variation of field that we see moving along the trajectory close to Jupiter. And we've seen that now on subsequent periapses, and of course this is just a notional representation, but it's very significant because when we see this kind of small spatial scale variation, it indicates to us that we may be very close to the source. And so that might mean that the dynamo is above that metallic hydrogen region that you saw in Scott 3, and it may operate in the molecular hydrogen envelope above there. So that's very significant. But I'd like to turn to some of the observations of the aurora. If you can go to Jack 2, we have a little movie showing the ultraviolet emissions from the South Pole collected by the UVS spectrometer as it flew above the pole. This is the first complete image of the South Pole that we have, because, of course, all previous observations were made near the equator plane, never from atop Jupiter's polar region where we could stare down and look at the aurora. So this is an amazingly complex aurora in the South Pole. It has many components that we expected to see there. The very innermost circle you see is the main aurora. Then there are very substantial emissions around that main aurora, extending all the way down to the emission that you see just to the left in this still, which is Jack 3. That's caused by an interaction with the satellite Io, the innermost satellite in Jupiter's magnetosphere. And that long tail extending past Io, that simply traces out Io's orbital motion about Jupiter. And the very significant thing about this figure are the reds and the whites and greens. Those colors represent a different path length through the atmosphere for these photons, these ultraviolet photons. And inside the main aurora, we see emissions that are largely red. That line between the red emission and the white emission, that follows the sun around and illustrates a solar wind control of the aurora that we were not quite prepared to expect. But more significantly, it looks like we can interpret those reds and whites in an entirely different way than we have previously. It looks like the red emission might evidence electrons being sucked out of the atmosphere instead of precipitating in. And we normally attribute auroral emissions to electrons precipitating down onto the ionosphere. But instead, it looks like some of these emissions are actually driven by electrons being pulled out of the atmosphere. So that's intriguing. I have to move now to my final graphic, which is Jack 4. I want to talk just briefly about the trip from Earth to Jupiter We spent 5 long, cold years in space in transit to Jupiter. During that time, the star cameras that we use to provide attitude information for the magnetometers, they looked out into space continuously, and occasionally they saw things flying by that weren't in the star catalog. And what we found is that we could track some of those objects, and indeed they were excavated from the solar panel by the impact of dust particles. Now these are tiny particles. You could fit 100 of them on the head of a pin, but they're traveling at enormous velocity. They're 10 times the speeding bullet. And so they excavate little pieces from the spacecraft, and those float off, and we see them in reflected sunlight. So it turns out that we can use this spacecraft and its prodigious 60 square meters of solar array as the largest dust detector ever flown in space. And so we're sensitive to particles that are larger and more infrequent than those that can be measured in space by a dedicated dust detector. So that's exciting. Not to worry, the spacecraft is operating fine. It turns out all spacecraft traveling this path are pelted with numerous impacts. We recorded close to 1,000 of them on the way out, and we're still operating fine. We're just the first spacecraft that's able to see what happens. So I'd like to turn this over now to my colleague Heidi Becker to talk about the radiation environment. Heidi?
Thank you, Jack. And to start, I'd actually like to keep on the theme of star cameras and share a very special picture with everybody that we took with our Stellar Reference Unit, which is the spacecraft star camera. This is our navigation camera that takes pictures of the stars to guide our way. So if everyone would go ahead and start Heidi 1, which is our animation, what you see is where we took this image, and it was in a very special place. What you're seeing is Juno flying in between the narrow gap between the planet and the radiation belts. And as we turned out, the star cameras took this picture. And if you go to Heidi 2, you'll see the still of that. And what you're looking at is the view of the constellation Orion from inside Jupiter's ring. And this is the first image of Jupiter's ring that has ever been collected from the inside of it looking out. Juno is 3,000 miles from the planet when we took this picture, and what you're seeing here is the main belt of Orion in the center, or in the main belt of Jupiter, actually, main ring, in the center of the image. And the bright star in the upper left is Betelgeuse, and the 3 bright ones in the lower right-hand side of the image is Orion's belt. So what you're looking at here is a ring of dust that's 40,000 miles away, and stars that are hundreds of light years away, all in the same picture. And if you go to Heidi 3, we've connected the dots for you, so you can see Orion there. It's very recognizable. This is what it looks like when you see it from Earth, and we thought it would be nice to share with everybody that you could be 500 million miles away from where we stargaze at Earth and look at this, stargazing from Juno. And heaven looks the same to us from Jupiter. So, and there's no radiation in that picture, but that isn't true everywhere at Peridot. So if you will go to Heidi 4 and play this animation, you can just keep playing this as I explain it to you. This is an artist's rendition of Juno's Peridot 1, which is our first pass close to the planet, and you see we're just grazing the inner edges of the radiation belts. We go through that gap. Now we know for sure that gap is there. We were counting on it. But no spacecraft has ever flown that close to the planet. No one has ever been that high in the inner edge of the radiation belts. And like everything else with Juno, the radiation environment was different than we thought it would be. And the closer we got to Jupiter, the more different it was than we thought it would be. And as a matter of fact, when you hit those inner edges there that you see in the animation, the high-energy electrons that get into our instruments and degrade and create noise, the number of those was 10 times less than what we thought it was going to be, which is very great news from an engineering perspective. It's great for science. All the radiation belt modelers are going to have a lot of data to work with, and this is something we never could have known without going there. Now, this is just one piece of our orbit, and we know we're going to get into harsher places later on. But I also want to let everybody know that Juno's very healthy and doing great, and the suit of armor is working. So with that, I'd like to hand it over to Candy, who'll tell you about JunoCam.
Thank you, Heidi. I'm going to be showing some data that we collected just last Friday. So just last Friday, Juno passed close to Jupiter on what we call Perigove 6. And what you are looking at, look at Candy Hansen 1. Those are 14 JunoCam images that we collected as we flew through that 2-hour pass from the North Pole to the South Pole. So the image on the left is looking straight down at the North Pole. It's half lit, as Scott was describing. The North Pole itself is approximately in the center, and you're seeing all of Jupiter. On the far right, on the right-hand side, we're looking at the southern hemisphere, and again, we're far enough away from the planet that you see all of Jupiter in our field of view. Now, the interesting thing is what happens as we zoom in, and these 14 images, the width of the image is the width of the JunoCam field of view. But we collect our images as the spacecraft spins. So as the spacecraft gets closer and closer and closer to Jupiter, we see less and less of Jupiter itself in terms of area, but we see more and more detail in the pictures. And so I'm going to actually show you the fourth image in the sequence from the left to start with, and then the fourth from the right. So just picking out 2 of those 14 to look at in this higher detail. So if you go to Candy 2, this is taken at approximately 38 degrees north latitude, and you can see a big wavy band of clouds in the middle of the image. If you go to Candy 3, I'm drawing your attention to those clouds. And then in Candy 4, it's really just a cutout of that same image. But there's a couple of things I wanted to point out here. So we've got these big wavy clouds, but then you can see tiny little white dots. They look tiny just because Jupiter is so big. These are actually clouds that are about 50 kilometers across. They are up above the cloud deck. We know that because we can actually see them casting little tiny shadows. And we've seen this actually before in some of our earlier images, but in this particular Perigove, the lighting is really good to see these features. And we have our camera settings dialed in, and honestly, we were so enchanted by the poles that we're only now just starting to look at other places on the planet. So these look almost like squall lines. If you go to Candy 5, this is an image taken now in the southern hemisphere. This is the South Tropical Zone, and again, I'm going to go to the cutouts that show you in more detail what we're looking at. So Candy 6, and then stop at Candy 7. Here you can see again that it's a really stormy day on Jupiter. We've got these little white storm systems really just scattered across the entire South Tropical Zone. Again, they're about 50 kilometers across, which is, so I keep saying tiny, but they're really not tiny at all. And they're up above the cloud deck at a pressure level where the temperature is going to be very cold. And so what you're seeing is most likely ice crystals of water ice and ammonia ice. I want to mention that these images that I just showed were processed by 2 of our amateur citizen scientists, Gerald Eichstadt and Sean Doran. They have processed quite a number of our images, but it's really the whole endeavor of JunoCam was to find ways for the public to participate in a meaningful way on a flight mission. So with that, I'd like to draw your attention to Candy Hansen number 8. And what you'll see is across the top, I've got 4 images of Jupiter. This is just 4 of many images that our amateur astronomer community has contributed. So on our website, we have a way that the community can upload pictures taken from their backyard telescopes. That's the top row. Then we take those images, and again, many more than 4, and we make a cylindrical map, which is what you see along the bottom. Then for a given perijove pass, and in this case it's number 6, we ask the public to define points of interest, places they think would be good spots for pictures. And so that's what the yellow circles represent. And the 2 images that I just showed you are the ones that are covered by those green circles. So we the public voted on what to take pictures of. We ended up with those. And so our whole citizen science endeavor, I think, is turning out to be quite interesting. The last chart, Candy Hansen 9, we love to see artistic products in addition to the more rigorous renditions of color reconstruction and so on. And the thing about art is that it captures feelings that either you don't recognize in yourself or maybe you don't know how to express. And for me, this image captures how I feel to be a part of this project. And I'll just mention this was processed by Myrna. With that, I'm going to turn it back to Scott to give us a little bit more.
So thanks, Candy. I'm always amazed at looking at those pictures. The idea of seeing those little cloud features, those white caps coming out of Jupiter, I mean, they're full of ammonia and water ice, and you know what you're really watching is it's snowing on Jupiter, and we're seeing how it works. And so I can imagine myself flying around in that atmosphere while it's snowing, and it's really great to be able to project myself and use that imagination and understand how another whole world works. Some things are similar, and a lot of things are different. And you know, your last picture of the art really shows how people are able to artistically express themselves, and it's so great that we can do that and enable that with the Juno. We have a big campaign with Juno for public awareness where we're trying to inspire and motivate the connections between science, art, and music. And a lot of the images that are being made on our website by the public are actually artistic. Some of them are science, and a lot of them are artistic, and it's great to see that. And that whole collaboration that we do extends into music, and we've formed a collaboration with Apple, and we've made some music that's Juno-related, and Apple's helped us distribute that. And what I'd like to play for you next is some sounds that we got, that we received on PJ4, the 4th time we flew by Jupiter. And we've been studying those, and we want to share them with you, because they really echo and demonstrate this connection between science, music, and art, in the sense that these sounds sound a lot like musical notes. So you can take a listen to nature's music here with going to Scott Bolton slide 7. Now that's a audio video file. So I'd like to go to Scott Bolton 8, sort of to close. This is a picture of Jupiter that's also posted on our website. We open it up to amateur astronomers who help us actually plan out the JunoCam images. And this was taken by Christopher Go and posted. It's a pretty recent picture of Jupiter. And what I wanted to show is this looks like the Jupiter that we know and love. It's got the zones of belts and the great red spot, and I want to extend an invitation to all of you to join our team as we look forward to the very next close polar pass by Jupiter, when we'll be targeting that great red spot. Now, that great spot's moving around, so it's not the easiest thing to target, but on July 11th, we're targeting to fly right over that. So stay tuned, and you can join us on July 11th.
Magnificent. Juno has taught us a great deal about Jupiter over the last 12 months, and the spacecraft will continue its mission through 2018. Juno will then descend into Jupiter's atmosphere in a controlled dive at the end of its mission. Thank you for watching. Please share this program with your friends and members of your local astronomical society. Until we come back next month, good evening.